Hello and welcome back to Math with Mrs. Becker. Today we are looking at college algebra, the second part of chapter 1, section 5. What we will be doing today is taking two functions and creating a new one through a process called composition. And so here's how this looks. If I have x composed of g of x, what this means is I would take the f function, keep everything the same except for the variable. Where the variable is, you are going to replace it with the whole function g of x. If I have g composed of f of x, this time the g is first. So whatever function is listed first, I call that the skeleton function. So that's the outside. So you would rewrite it, but where the variable is, you would replace the variable with the full function f of x. Now there's a couple ways that you can write this. If you want the f to be the skeleton function, the outside, and g to be the guts, you can write it like this. Or you will see it like this. These two things mean the same thing. It means take the f function, fill the g function into the variable. Here as well. This means the same thing as this. Take the g function, fill the f function in for the variable. So let's go ahead and get started. If I have f of x and it's x plus 2, and I have g of x and that's 4 minus x squared, if they want me to evaluate f composed with g of x, f is stated first. So the f function is x plus 2. But notice instead of writing an x, I put parentheses because in the place of x, I have to plug in the entire g of x function, which is 4 minus x squared. I don't have any exponents here. I don't have anything to distribute. So this actually looks like this, okay? The parentheses did not have any use there except for knowing where to put that function. I can combine my like terms. So I would have negative x squared, 4 plus 2 is 6. That is called a composite function. You took the g function, filled it into the variable for the f function, combined your like terms, and that's what we get. Just like we could do when you had operations of functions, now we can do evaluating. We can replace the x with 0, 1, 2, and 3. If I put in a 0, so it would look like this. F composed with g, but x is replaced with a 0. Negative 0 squared plus 6. Now the negative is not in parentheses. So what that means is you're multiplying by negative 1. So order of operations, you square the value, then multiply by a negative. 0 squared is 0. 0 times a negative is still 0. 0 plus 6 is 6. Now, f composed with g, what if x is a 1? Negative 1 squared plus 6. 1 squared is 1. 1 times a negative is negative 1. Negative 1 plus 6 is 5. F composed of g, what if x is a 2? Negative 2 squared plus 6. 2 squared is 4. 4 times a negative makes it negative 4. Negative 4 plus 6 is 2. F composed of g, what if it's a 3? Negative 3 squared plus 6. 3 squared is 9. 9 times a negative is negative 9. Negative 9 plus 6 is a negative 3. So we were able to perform a composition of two functions to create a new function. Then we could evaluate that composition for various values of x. Let's look at this one more time, but now we're going to go ahead and go in reverse. I'm going to take the g function as the outside, and I'm going to replace x with f of x. So g is 4 minus, there's where x is, so I'm going to go ahead and put parentheses. Here is, I call this the skeleton. It's 4 minus the variable squared, where the variable was. Now we have to replace it with the f function. That is x plus 2. Now this one's a little bit more work because I have a power of 2. So 4 minus, I'm going to go ahead and put brackets here because now I can actually write out that binomial 2 times. Remember, when you have a power of 2 on a binomial, it means that you have that group twice. I need to FOIL this. 4 minus x times x is x squared. x times 2 is 2x. Inside, 2 times x would be 2x. So when I went to combine those, 2x plus 2x would give me a 4x. Last, 2 times 2 is 4. Now here's the kicker. You are minusing x plus 2 squared. So you have to make sure that you subtract every term that you got from squaring your x plus 2. All that means is to make sure that you distribute the negative to every term. 4 minus x squared minus 4x minus 4. If I combine the like terms, negative x squared minus 4x. 4 minus 4, that cancels. This would be our new composite function. Now they want us to go ahead and evaluate it. So this is g composed of f. What if x is a 0? So negative 0 squared minus 4 times 0. 0 squared is 0. 0 times a negative is still 0. Minus 4 times 0 is 0. 0 minus 0 is 0. If I have g composed with f and x is a 1, negative 1 squared minus 4 times 1. 1 squared is 1. 1 times a negative makes it a negative 1. Minus 4 times 1 is 4. Negative 1 minus 4 more is negative 5. G composed of f, what if x is a 2? Negative 2 squared minus 4 times 2. 2 squared is 4. 4 times a negative is negative 4. Minus 4 times 2 is 8. Negative 4 minus 8 more, that's a negative 12. G composed of f, what if x is a 3? Negative 3 squared minus 4 times 3. 3 squared is 9. 9 times a negative is negative 9. Minus 4 times 3 is 12. Negative 9 minus 12 more is a negative 21. So we just performed 2 composition functions, and then we went ahead and used the new functions to evaluate, okay? Obviously, they're not all going to be quadratics and linear functions. You might end up with radicals. Oh, there we go, guys. Sorry. We might end up with radicals. Now this, don't worry about this. I think that was a typo on my part. Here it says f of x is the square root of x. Because you can never have a negative underneath the radical, this is the domain. It means that the x values that you can plug in have to be greater than or equal to 0, okay? This is a linear function, so its domain is all reals. So sometimes they'll say, if it's possible, do this. And what that means is go ahead and find the composition. If you end up with a negative underneath the radical, then it's not possible, so it'd be undefined. But if you could fill a 2 in and be able to finish out the calculation, you're good to go. Okay, so let's take f square root, there's the x, so I put parentheses so I remember where to fill that value in, or that function. The function I'm filling in is g, so it's x minus 1. Well, this is the square root of x minus 1. That's what f composed with g is. Now, they say if it's possible, go ahead and calculate a 2. Well, if I look, I can totally put a 2 under there. 2 minus 1 is 1, and the square root of 1 is 1. The only way that you could not do that is if, let's say I was putting in a 0. 0 would be undefined because 0 minus 1 was a negative. So that's what it means if they say if possible. There will be times where this answer might end up being undefined. Okay, let's look at another one. The g function followed by the f function. So g is x minus 1. Where I had the x, I went ahead and filled in the parentheses. What goes in that place is the square root of x. So it's the square root of x minus 1. That's the function. Now, if possible, put in a 0. Well, again, I can plug a 0 in there. The square root of 0 is 0. 0 minus 1 is negative 1. Okay, so that's that part. Now, if I am composing f of g for these two, here again, I'm going to have a domain limitation. It says we have to find the domain. Well, the domain of f of x, the domain of f of x is all reals because this does not have a fraction, it does not have a radical. Here, though, whatever's underneath the radical, so in this case, 9 minus x squared, that has to be greater than or equal to 0 because you cannot have a negative. So if I go to solve for x, if I minus the 9 to the other side, divide both sides by negative 1, Anytime you divide by a negative, remember you have to flip the sign. So now what I have is x squared is less than or equal to 9. To cancel the power of 2, you have to take the square root. Anytime you cancel a power of 2, you have to include both the positive and negative. The square root of 9 is 3. What this actually means is I have a positive 3 and a negative 3. They are included, so it's a filled-in circle. X has to be less than. Remember back in Algebra 2, we said the funny and or. Great or then symbol means it's a disjunction. Less than means it's a conjunction. This is less than, so it means I'm shading in between. So our domain, our x's have to stay in between and including negative 3 and 3. Okay? They want us to find the composition. If I take the f function, where the x is, I put in parentheses squared minus 9. Where x was, I'm filling in the g function. So it's the square root of 9 minus x squared. When I go ahead and I calculate this, if I square a square root, that's going to cancel. But remember, when the symbol cancels, it never changes what's underneath. So the 9 minus x squared stays. If I combine like terms, positive 9 and a negative 9 cancels. So what I have is negative x squared. Now, if I go ahead and graph this, what would happen, you guys, is it's super cool. 1, 2, 3. Okay, this is a parabola flipped upside down. But when you actually go and graph it, it does not go forever and ever. It's an upside down parabola that has to stop when it hits negative 3 to 3, because that's the domain. If you have a value that's less than 3 or greater than 3, my g function does not exist. Okay, so the g function would no longer be real. It would be imaginary. So this domain carries through all the way. If you sketch this on Desmos, if you went ahead and put this in just like this, open a parenthesis, square root of 9 minus x squared, close a parenthesis, square minus 9, right away when you look, you would see a parabola flipped upside down. When you slit up, you would see that it stops as it goes all the way to the left 3 and all the way to the right 3. Kind of cool. Okay, there are times where you can take G, fill it into F, and then take F, fill it into G, and you get the same solution. So that's what we're going to do right here. One thing, I do not like G of X like this. I just figure let's go ahead and distribute. Why deal with parentheses when I know I'm going to add additional parentheses as I do the composition? So 1/2 times x is 1/2 x minus 1/2 times 3 is 3/2. Here, F is the outside, so it's 2, open parentheses, plus 3. G is the inside, 1/2 x minus 3/2. 1/2 times 2 is 1x. If I multiply here, remember, anytime you multiply by a denominator, it cancels. So this 2 would cancel this 2, leaving you a negative 3, plus 3 is on the outside. Well, negative 3 plus 3 cancels, so I just have an x. Now let's go the other way. So take G, it's 1/2, there's the x, minus 3/2. Where the x was, I'm filling in 2x plus 3. 1/2 times 2x is 1x. 1/2 times 3 is 3/2 minus 3/2. Positive 3/2 minus 3/2, that cancels. So you ended up with the exact same thing, whether you had F on the outside or G on the outside. Kind of cool. So that can happen. It's not common. In fact, this only happens when these two functions are inverses of one another, and that's something that we'll talk about in a section coming up. Now, if you ever plan on taking calculus, it is important to be able to decompose these functions. So what we have been doing is taking two functions, putting them together to create a new one. What happens in calculus is they will give you the composition, and you have to figure out what was f of x and what was g of x. Now, f of x, I call that the skeleton. It lays out the frame. What are the basics? Then g of x, that's the guts. What was put in for x? So here's an example, f of x. Now, if I look at the basics, what I need in this problem, I need a power of 3. So it's x cubed. G of x, the guts in the place of x, I filled in 3x minus 5. That's it. If I took these two functions and I replaced x with 3x minus 5, it would match that. Okay, here's another one. If you have a fraction, you have to set that up in the f of x. So I have a 1 on the top because that's the framework. On the bottom, I need to have a power of 2. So your skeleton is 1 over x squared. But g of x, instead of just having x squared, we filled in x minus 2. One more to make sure we've got it. F of x, again, I have a fraction. To get a 1 on the top, that needs to be part of the skeleton, part of the framework. The bottom needs to have a square root. So my f of x is 1 over the square root of x. G of x, well, instead of just an x under the square root, we had 3x plus 1. Okay, those are examples of decompositions. We're going to end today with a real-life example of when you might need to use compositions of functions. It says the number n of bacteria in refrigerated food is given by this function. Okay, T is the temperature in degrees Celsius. Now what this means, this is the domain. So that means this function is accurate for the temperatures, the degrees Celsius from 2 to 14 and including those values. If the food has a temperature between those two values, this is an accurate way to figure out the number of bacteria, okay? Once you take the food out of the refrigerator, the temperature of the food is given by this function, where T, it's accurate from 0 to 3, it represents the time in hours, okay? They want us to find the composition N, so we want to find the number of bacteria. Whatever's on the outside, that's what you're trying to find. So we're trying to find the number of bacteria. The most inner variable, that's what it's based off of. So the number of bacteria based off of the time in hours. Let's go ahead and do that. So N is the outside. So 20, there's a variable, squared, minus 80, there's a variable, plus 500. In the place of T, we're putting T of T. We're putting 4T plus 2. 4T plus 2, 4T plus 2. Now this is a power of 2, so again I have 20. I have to take 4T plus 2. I have 2 of those. So that's why I put the brackets, to make sure that I remember that I have to distribute this 20 into all of this. So it's 20 outside of 4T times 4T is 16T squared. 4T times 2 is 8T. 2 times 4T is also 8T. 8T plus 8T would combine to 16T. Last, 2 times 2 is 4. So I can go ahead now and distribute. 20 times 16T squared, 320T squared. 20 times 16T, 320T. 20 times 4, 80. Now I'm going to go ahead and distribute this negative 80. Negative 80 times 4T, negative 320T. Negative 80 times 2, negative 160, plus 500. So our number of bacteria based off of time is 320T squared, positive 320T, negative 320T cancels. 80 minus 160 plus 500 is 420. So now this is easier. You can keep track of the number of bacteria in the food based off of how long has it been out of the fridge. That's a lot easier than the original where you had to temp everything. So sometimes compositions help just to make everyday real situations easier. If you want to find the number of bacteria, if T is 2, I go ahead, T represents the number of hours, so if it's 2 hours, 320 times 2 squared plus 420. So 320 times 4 plus 420, you would get 1,700 bacteria. That would be the bacteria count of food that was in the fridge. You took it out. It's been sitting on the counter for 2 hours. Let's say that there's a rule, maybe at like a hospital or a daycare center, where when the bacteria count reaches 2,000, they must throw the food away. They would need to know, okay, well, how long can we take it out before we need to chuck it, okay? So you want to set this equation, this is the number of bacteria, when would it equal 2,000? I just have to solve for t. So if I take 2,000 minus 420, this is 1,580 equals 320t squared. Divide by 320. So 1,580 divided by 320 is 4.9375 equals t squared. To cancel a power of 2, you take the square root. Now, typically, you would have to include both a positive and a negative. However, this represents time. We don't have a negative amount of time. So when I do this, I'm just going to take the square root of 4.9375 and I include the positive value. It's approximately 2.22 hours. That concludes 1.5. There is a quiz tomorrow. The quiz is over sections 1.4 and 1.5. So you are looking at transformations. Make sure that you know the rules for transformations. Okay, that's a really big thing to be successful with this quiz. So make sure you know your transformations. 1.5, those were operations of functions. So adding, subtracting, multiplying, dividing, and then today we added compositions. I hope you had a great time. I'll talk to you soon.